when two systems are at the same temperature, they are said to be in thermal equilibrium because there won't be any heat exchange between the two systems. A and C will become in thermal equilibrium and B and C will also become in thermal equilibrium, which means that indirectly A and B will also be in thermal equilibrium. This system will have some sort of energy, and that particular energy is known as internal energy. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter here today, that is thermodynamics. So thermodynamics just means that the transfer of heat, how heat actually affects various things, how it is governed by various laws, and everything will be discussed in this particular chapter. So let's get on to it. So before getting into any of the laws which govern thermodynamics, we have to know what is thermal equilibrium. Again, every system has a tendency to be in equilibrium. So what is thermal equilibrium? Thermal equilibrium means that we say that a system, let's say this is two systems, system A and system B. Again, we use the term system and surrounding in order to classify this particular observation. That is, if we are observing a teacup, that is, this is our teacup. Let's say this is our teacup. Then we say that this particular arrangement is our system. And anything outside the system will make the surrounding. So anywhere around this system, that is the atmosphere or a table or a room, whatever it may be, that will make the surrounding. So we say that system plus surrounding together makes the universe. So that is not there for you to study or anything, but it is very good to know that system plus surrounding together makes universe. So basically in a nutshell, we can say that system is just where our observations or the experiment or just our analysis is taking place. And anything around that particular system is known as its surrounding. So system plus surrounding will give you the entire cosmos or simply the entire universe. So I have two systems here, system A and system B. Let system A be filled with hot water or just a cup filled with hot water, and system B be a cup filled with ice, so that there is a temperature difference between them. So again, we are generalizing that, okay, this is system A and system B. In practicality, it can be any system. It can be a cup of coffee, it can be a big room, it can be earth, it can be anything you choose to observe. So in this particular case, there are two systems, system A and system B. So what thermal equilibrium states is that if there is a temperature difference between A and B, then there will be heat flow between the system. That is, there will be heat exchange between the systems in such a manner that the difference in temperature is adjusted until both of their temperatures are equal. That is, if this was at 25 degrees Celsius and if this was at initially 10 degrees Celsius, then the heat exchange will take place until both of them are at, let's say, equal temperatures. So then we can say that when they are in equal temperatures, when the heat flow is cut off, then we say that both systems are in thermal equilibrium. So in definition, we can just say that we say two systems are in thermal equilibrium when there is no heat flow between the system. Or simply we can also say that when two systems are at the same temperature, they are said to be in thermal equilibrium because there won't be any heat exchange between the two systems. Now, since we know how heat works, what heat transfer is, what is heat and what is thermal equilibrium, we have to learn a few laws that govern thermodynamics. So there is actually three laws, there is actually four laws, that is zeroth law, first law, second law and third law. Together they make the governing bodies of thermodynamics. Why is it 1, 2, 3 and 0 and not 1, 2, 3, 4 is because we actually found out the first law first, the zeroth law second, the second law third and the third law fourth. The reason why we named it as such is because Somebody found out the first law initially and said that, okay, this is the first law of thermodynamics. But later it was figured out that, okay, there is a fundamental, more basic law rather than the first law. So there was no other choice but to name it as zeroth law, because it was a more fundamental law for thermodynamics. That is why we named it as zeroth law of thermodynamics. Now, what does zeroth law state? Okay, zeroth law states that if you have two systems, let's say like this, there is system A and system B. There is system B and system C. So we are saying that, okay, A and B are in thermal equilibrium, meaning there is no heat exchange between them. And B and C are also in thermal equilibrium. Then we can say that A and C will also be in thermal equilibrium. That is what it evidently means. So to put it in a nutshell and make it more simple, we can say it like this. That is, let's say Hari and Vishnu are in the same class. So Hari and Vishnu are in the same class, and Vishnu and Irene are also in the same class, which means that Hari and Irene are also in the same class, right? If Hari and Vishnu are classmates and Vishnu and Irene are classmates, then it means that Irene and Hari are also classmates. All of them are studying in the same class. Just like that, we can say that if system A is in thermal equilibrium with B and system B is in thermal equilibrium with C, then C is in thermal equilibrium with A. That is zeroth law of thermodynamics. Now, why does this weird law take place is because there are certain things that block heat transfer. That is, if we had a system which was large like this and the shape of the system is like this. This is system A, this is system B, and this is system C. And I'm saying that, okay, there is no heat transfer between A and B. That is, I made the walls very special so that heat cannot travel from A to B. Then what will happen? There is no heat transfer between A and B. We don't know what happens between A and B because there is no energy transfer between A and B. These kind of walls is actually known as adiabatic walls. Adiabatic walls, which do not allow heat transfer to take place. Adiabatic wall means that there is no heat exchange between the system and the system because it is separated by an adiabatic wall. Adiabatic wall prevents heat transfer. And now this particular wall will allow heat transfer, which means that system A and system C will exchange their heat. Just like that, system C and system B will also exchange their heat. So since it is allowing heat exchange to take place, we call it as a diathermic wall. Again, you don't have to understand what is the special nature of diathermic wall or adiabatic wall. You just have to understand that adiabatic wall prevents heat transfer and diathermic wall will allow heat transfer to take place. So again, A and C will become in thermal equilibrium and B and C will also become in thermal equilibrium, which means that indirectly A and B will also be in thermal equilibrium, even though there is no direct contact between A and B. So this was actually classified as the law that is known as zeroth law of thermodynamics. In words, we can write it down as, so in words, we can actually define the zeroth law as when a body is in thermal equilibrium with another body. Namely, we can choose examples, that is, when a body C is in thermal equilibrium with a body B and another body, which is A, is in thermal equilibrium with body B, then we can say that A and C will also be in thermal equilibrium with each other. That is, to put it to simple terms, again the figure comes, that is, you can use any figure you choose that is appropriate. So we say that Okay, this is separated by an adiabatic wall, and there is A, B, and C. If A and C are in thermal equilibrium with each other, and C and B are in thermal equilibrium with each other, then indirectly A and B is also in thermal equilibrium with each other. So that is known as zeroth law of thermodynamics. And it is very important that you note that the thermometer also works on the basis of zeroth law of thermodynamics. Now, the very next important topic is internal energy. So, internal energy is denoted by U, and capital U denotes internal energy. So, what is internal energy? We know that any system inherently possesses some energy. That is, every system will contain some sort of energy. If a body is kept somewhere, it has potential energy. If it is moving, it has kinetic energy. Like that, every system will have some sort of energy. Rotational, vibrational, all kind of energy, translational, right? So if I am taking a gas inside a container, let's say this is a container with a movable piston like this. So this is a piston arrangement which can move up and down. So inside this arrangement, I place several gas molecules like this. So I place several gas molecules like this inside this particular chamber. So now I'm saying that, okay, this is a movable piston inside which I have filled some gas. So this particular gas itself is my system. So this particular system which is containing gas is what I'm going to observe. Now I'm saying that, okay, this system will have some sort of energy, and that particular energy is known as internal energy. So the internal energy of this system will be equal to the individual or sum of the kinetic and potential energies of the individual molecules of this particular system. That is, each molecule will possess a kinetic energy or a potential energy. So if I take the sum of entire kinetic energy and potential energy of this particular system, then I can say that, okay, it will be equal to the internal energy of my system. In reality, it is the sum total of all the different type of energies, that is vibrational, kinetic, translational, potential. Every type of energy will be accumulated, and the sum of those energies will be equal to internal energy. But for us right now, we only need to know that the sum of kinetic and potential energies will be equal to the internal energy of a system, and we denote that by U, or simply we use delta U in order to specify small or very small change in internal energy. And how can we affect this particular internal energy? That is, I want to increase or decrease the internal energy of a system, I have to affect KE or PE. That is, internal energy is equal to sum of kinetic and potential energy of the system. So we have to adjust or influence the kinetic or potential energy of the system in order to change its internal energy. So again, how can you influence the kinetic and potential energy of a system? Obviously, we only have to influence one, automatically the other will be influenced. So if I give heat to this particular system, what will happen? This thermal energy or simply heat will be absorbed by the individual molecules, and they will try to move even faster. That is, when you expand a gas, when you heat a gas, it expands, which means that these small molecules will be hitting on the walls of the container, which causes the piston to rise up. So the gas is expanding. The gas can only expand when the molecules are moving at a higher speed rate, hitting on the walls of the container, which means that the gas is expanding. So again, this all happened because I gave heat to this particular system, or simply I changed the temperature of this particular system, or simply I affected the kinetic energy of this particular system. So we can say that internal energy will be affected by temperature, or simply if you increase the temperature of a system, you can actually increase the internal energy, or simply change in temperature will affect change in internal energy. So coming to the next topic, that is the first law of thermodynamics. What is first law? So first law states that if I give heat to a particular system, that is, again I am giving heat to a particular system, This arrangement is the same arrangement as before. That is a chamber that is filled with gas, which has a movable piston that is connected at the top. So again, if I give heat to a system, what happens? Its internal energy changes, right? The temperature causes change in internal energy. Or simply, if I give heat to a system, the internal energy changes. So what first law states is that if I give heat to a system, that particular heat is used, or that particular energy is used to increase or decrease. Simply we can say that change the internal energy and to do some work on the surrounding. That is, heat given to a system is used partially to increase the internal energy of a system and to do some work. Again, the heat given to a system, heat given to, let's say, delta Q is the small amount of heat I am giving to this particular system. So heat given to this particular system is used to increase the internal energy of a system, and it is also used to do some work on the surroundings. Or delta Q is equal to delta U plus W. That is the first law of thermodynamics. So how does this all add up? That is, the heat, let's say 100% of energy I am giving to this particular system. So heat is given to this particular system. Then what happens is that partial of that energy, part of that energy is used to move up this particular piston. Again, I told you before that as internal energy increases, the molecules will try to slam on the container walls and will try to expand. So as it expands, the piston rises up, which means that it is doing a work. The system is doing a work on the surrounding. So again, in physics, when the system is doing a work on the surrounding, we take it as negative. So it is considered as negative work. So we can say that from the delta Q energy we supplied, we have to subtract that amount of energy which was used for work. So delta W is subtracted because whatever heat was given to the system, part of that heat was used to do work on the surroundings. Now, the remaining portion, let's say 30% of this was used as work. Out of the 100% of energy I gave, 30% was used to do work, which means that how much energy is remaining will be used to increase or decrease the internal energy or to cause change in internal energy. So we can say that the remaining energy will be used to produce a change in the internal energy of the system. So the first law of thermodynamics states that the heat given to a system is partly used to do work on the surrounding, and the remaining energy is used to increase the internal energy of the system. So again, the system is doing a work on the surroundings. That is taken as negative. If the surrounding is doing a work on the system, that is taken as positive. In chemistry, it will be ulta, but again, it is very important that you understand the definition of first law of thermodynamics because we need it throughout this particular chapter. Delta Q is equal to delta U plus W. So again, in terms, we can say that heat supplied to a system is used to increase the internal energy of a system and to do work on the surroundings. And it is given by the equation delta Q is equal to delta U plus delta W. And again, one more thing, what is this delta W? That delta W is the small amount of work that is done by the system to the surrounding. But again, this delta W, earlier we saw that delta W is equal to P delta V. That I told you I'll explain in thermodynamics section. So how exactly do we get this particular equation? So again, the reason why we are getting this particular equation is that because we are considering a gaseous medium which is doing a work. So that is why a fluid medium which is doing a work. That is why we are taking pressure in terms of work. So what happens is that again, you have a container which is filled with gas. So when you give heat to a system, what happens is that this will do some work. The gas molecules will do some work in order to increase the height of the piston. It is just pushing the piston walls so that the piston goes up. So how much up will it go? Let's say that it is going up by a distance of delta x. That is, again, you're heating up a container which is filled with gas with a movable top part. So when it gets heated up, it only rises slightly, not like it is going to explode or anything. Let's say that it only rises slightly for a small amount of temperature change. So that means that it raised by a displacement of delta x. And I'm assuming that the entire area of this particular piston is given by A. So again, what is the equation for work done? Work done is equal to force times displacement, or Fs, or simply Fs cos theta. So let's assume that since both the directions are same, we'll take cos theta as 1, as theta is equal to 0 degrees. Again, you don't have this derivation, but you need to understand where the equation came from, and I promised you that is why I'm doing this. So again, for small amount of work done, I can say that delta W will be equal to F delta S. So S is displacement, and that particular displacement here is delta X. Now, this particular F is force. Now, since we are talking about a fluid medium here, I am going to express it in terms of pressure. So we do know that F by A is equal to P, or simply F is equal to PA. So we can say that instead of F, I can actually use P and A, where A is the area of this particular piston. So delta W will be equal to P A delta X. Now, what is this A into delta X? A is the area and X is the, delta X is the displacement in the vertical direction, or simply the height. So if you take any object, like this, and if you multiply area times height, then you are bound to get the volume of that particular object. So again, if I do this, then I'm just indirectly measuring the volume that is risen here. So A delta X is nothing but delta V, that is the very small change in volume, or very small increase in volume. So that is how we get the equation P delta V, or simply delta W is equal to P delta V. You don't necessarily have to study this particular derivation, but it's a very simple one, and this is where the equation came from. Earlier I told you that we use the equation P delta V for work done. That is from this particular chapter, that is thermodynamics, and we use this particular equation because of this particular factor. So we can express work done as delta W is equal to P delta V. So why do we use that particular equation? In thermodynamics, we mostly deal with gaseous mediums or liquid mediums, that is mostly fluids. So in order to express the work done, it is much more simple to relate that to pressure and volume. That is why we use P delta V, or simply PV. And you might also note that it is also very similar to the equation, that is PV is equal to nRT, the ideal gas equation that you study in chemistry. So again, if delta W is equal to P delta V, then we can actually change one equation. That is, we know that delta Q is equal to delta U plus delta W. That is first law of thermodynamics. Now we have a substitution for delta W, which means that del Q is equal to del U plus P del V. So this is one more way of representing first law of thermodynamics. That is delta U is equal to delta U plus P delta V. One last thing to note about this particular equation, that is delta W is equal to P delta V, is only applicable. It is only applicable if pressure is constant. It is only applicable if pressure is constant. If pressure is changing or it is a variable quantity by any chance, then we cannot use this particular equation, and we have to use a different mathematical tool that is known as the one you already hate, that is integration. So from V1 to V2, the volume is changing, and if the pressure is also changing, then we have to use the equation that is P dV in order to signify the work done. So if it is constant pressure, we can use P delta V. If it is not constant pressure and if it is changing, then we have to use the integral form that is P dV. Very soon we will deal with that. So until then, we don't have to pressurize with that particular equation. So we'll move on to the next topic, that is thermodynamic state variable and thermodynamic path variable. So what exactly is a state variable and a path variable? So what is state? State of a system. The thermodynamic state variables actually means that it is the variables that is used to express the state of a system, that is mass, internal energy, temperature, volume, pressure, all these quantities, or density, all these quantities can be used to represent or explain or just define the state of a system that is in thermal equilibrium. So that particular quantity is known as a state variable. In simple words, we can just say that if we are describing a system that is in thermal equilibrium, that is known as a state variable. We have to use quantities like pressure, temperature, internal energy, density, mass, volume, etc. like this. So if we use these quantities in order to define a state of a system, that is known as state variables. So one more way of representing state variable is that it is a variable whose value only depends on the state of a system and not the path taken to achieve that particular state. So these words actually can be used to describe what is a state variable. Then again, in simple words, we can also describe what is a path variable. That is, if a variable whose value only depends on the path taken to achieve that particular value, then that is known as a path variable, and it does not depend on the state of that particular system, then it is known as a path variable. For example, I can say that the value of internal energy will change from value A to value B, but we are not concerned about the way that particular change happened. Maybe it went to a higher temperature, then to a lower temperature, then to a higher state, then to a lower state, and finally achieved B. But we don't care about the path taken. We only care about the initial and final values of the system. So if it is only dependent on the initial and final state of the system, or initial or final values, then we say that it is a state variable. And if it is dependent upon the path taken, then we say it is a path variable. Now we are going to do our first derivation of this particular chapter, that is known as Mayer's relation. So what exactly is Mayer's relation? Before getting into Mayer's relation, I want you to refresh one small derivation we did in the previous chapter, that is heat capacity. So heat capacity was indicated by S in the previous chapter, but in this particular chapter, that is thermodynamics, we are using C in order to represent that. Both are the same quantities, but due to different branches colliding, we are using different symbols to represent them. But both of them have the same meaning. That is, it is the heat that is required to raise any substance by 1 degree Celsius. So that particular ratio is known as heat capacity, and it is indicated by the letter C in thermodynamics, and it is given by the equation delta Q divided by delta T. So we are going to start our first derivation. So we are going to write down the first law of thermodynamics that states that delta Q is equal to delta U plus delta W, or simply we can write it as delta Q is equal to delta U plus P delta V, right? So again, if P delta V has to be written, then it is happening at constant pressure, which means that, okay, I'm saying that all of this process is happening at constant pressure. Now, I'm going to divide this particular equation, equation 1 divided by delta T. I'm going to divide throughout this particular equation by delta T. Then what will happen? Delta Q divided by delta T at constant pressure is equal to delta U divided by delta T again at constant pressure, plus P delta V divided by delta T again at constant pressure. Okay, then I can transform this equation into this particular form. So again, to obtain Mayer's relation, that is, a relation between heat capacities of systems, can be expressed or can be found out by starting from the first law of thermodynamics, which states that delta Q is equal to delta U plus W, which is written as P delta V. Now I'm going to divide all of this particular terms in the equation by delta T, and I am assuming that this process is happening at constant pressure. Then I can write it as such. But we already know that delta Q by delta T is equal to C, that is heat capacity. Now what if it is happening at constant pressure? Then very simple, instead of C we are going to write Cp. Cp indicating that it is happening at constant pressure. So Cp will be equal to delta Q divided by delta T, which is happening at constant pressure. So Cp will be equal to delta U divided by delta T plus P delta V divided by delta T at constant pressure. Okay, now again we are going to do one more transformation. Before that, I'm going to introduce to you the equation you all studied in chemistry, that is the ideal gas equation. So ideal gas equation states that PV is equal to nRT, where N is the number of moles, R is the universal gas constant, which is having a value of 8.314, and T is the temperature, P and V are pressure and volume respectively. So again, if I'm only considering 1 mole of substance, then N value I can take it as 1. So N is equal to 1. And since the volume here is changing, I can take it as delta V, which means that I'm saying in constant pressure, delta V amount of volume change occurs because there was a temperature change of delta T. So N again is 1. So it is equal to R into delta T, right? So P delta V is equal to R into delta T. So delta V means very small change in volume, and delta T means that it is that particular change in volume is caused by a very small change in temperature. So if I rearrange this particular equation, I can write P delta V divided by delta T is equal to R. That is universal gas constant. So P delta V by T, that particular relation is here, P delta V by delta T or P delta V by delta T, that is equal to R. So I'm going to substitute this particular R value here, which means that Cp is equal to delta U divided by delta T at constant pressure plus P delta V by delta T. P delta V by delta T, that is R. So we have this particular relation here. It is not yet done, you have to still bear with me. Till here we have a relation, that is Cp is equal to delta U by delta T plus R. We just have to convert this particular term also and we have a relation. So how can we convert delta U by delta T? So again, I'm going to write the first law of thermodynamics, that is delta Q is equal to delta U plus P delta V. Now, in this particular case, I'm only going to consider one thing, that is now the process is happening at a constant volume. So I'm saying that earlier it was pressure being constant. Now I'm saying that volume is being constant. So I'm saying that volume is constant. There is no change in volume. If there is no change in volume, then we can say that delta V, that is the difference in volume, is 0. Initial and final. Final minus initial is change in volume, which means that delta V, which is V2 minus V1, which is equal to 0, because V1 is equal to V2, because volume is not changing. So we can say that in this particular equation, P delta V will be equal to 0. That is, delta Q will be equal to delta U only, because P delta V will be approximated to 0. Now again, I'm going to divide this equation by delta T. So now I can say that, okay, at constant volume, that is at constant volume, at constant volume, delta Q by delta T is equal to delta U by delta T. Then again we know that delta Q by delta T is nothing but C, that is heat capacity. But since this is happening at constant volume, I can say that, okay, CV will be equal to delta Q by delta T. That is heat capacity at constant volume, where the volume is not expanding, but we are still giving heat to a system. So that can be expressed as delta Q by delta T. So this particular equation we are going to substitute here, because delta Q by delta T is CV, that is itself is equal to delta U by delta T. So instead of this equation, we can now write Cp is equal to Cv plus R, or simply Cp minus Cv is equal to R. This particular relation is known as Mayer's relation, that is Cp minus Cv is equal to R. There is one more relation which you don't have to derive or prove, but you still need to know that particular derivation, that is gamma is equal to Cp divided by Cv. This particular result you will use in the coming derivations, but for now you don't have to derive or prove or anything. Just know that there are two particular relations, that is Cp minus Cv is equal to R, which is known as Mayer's relation, and there is one more relation where gamma is equal to Cp divided by Cv. So the relation between heat capacity at constant pressure and constant volume is indicated as Cp minus Cv is equal to R in Mayer's relation. And there is one more relation which you don't have to prove or derive or anything, but you just have to know the result, that is gamma is equal to Cp by Cv. So that is two important things about heat capacity at constant pressure and constant volume. And one last thing you need to know about this particular thing is that what is extensive and intensive state variables. So what is extensive and intensive state variables? State variable again is used to describe a system that is in thermodynamic equilibrium. So what is intensive and extensive state variables? So extensive state variable is actually a state variable that depends on the size of the system. That is, if you have a system like this, and if you make it into a smaller system of 2, then the system itself is affected. The variables of that system is affected. Then that is known as extensive state variables, where extensive state variable depends on the size of the system, where intensive state variable does not depend on the size of the system. For example, mass. Mass is an extensive or intensive state variable. Of course, it is an extensive state variable, because if you cut this into 2, the mass of the system is now different, right? So mass is a extensive state variable. And what about volume? Again, volume also changes. So it is also an extensive state variable. Internal energy. Internal energy is the sum of kinetic and potential energies. So obviously number of moles will be less in both, which means that internal energy is also affected, which means internal energy is also an extensive state variable. And finally, temperature, pressure and density. If I have a cup of coffee, imagine that this is a mug of coffee. If this coffee is at 50 degrees Celsius, if I take it to 2 different cups, I am pouring this coffee into 2 different cups. Will the temperature change? No, of course not. Both will be still at 50 degrees Celsius, because the temperature won't change, because we are just changing the container. Even though it is distributed, the volume changes, the mass changes, the temperature of that system is not changing. So we can say that temperature is actually an intensive variable, intensive state variable. What about pressure? If this is at 1 atm or 2 atm pressure, if I change the container, will the will the pressure change? No, of course not. So we can see that it is also an intensive state variable. And lastly, density. Density of any quantity, that is unit density. If I take 1 kilogram cube of steel, and if I cut it into small pieces, each of that steel pieces will have the same density. Mass by volume is density, and that is constant for any metal or any substance we are choosing. That is, the density of water, even if I take in 1 cup or 10 cups, the density of water is 1 kilogram per meter cube only. It won't change. So just like that, even if we distribute it into 100 cups, or if the mass changes, the size changes, the density does not change for a given system. So we say that, okay, density is also an intensive state variable. So that much is about intensive and extensive state variables. So I hope you have understood everything about the introductory class to thermodynamics. I'll be back with more thermodynamics sessions. Thank you.